Okay, all of you go through this one more design problem on shear design of PSC beam. The support section of a pre-stressed concrete beam 100 mm wide and 250 mm deep. Width of the beam and depth of the beam is given. Let me write B is equal to 100 mm and overall depth is given as 250 mm, 50 mm deep. Is required to support an ultimate shear force of 60 kilonewton. Ultimate shear force only is given here. No need to multiply by 1.5 here. We ultimate shear force. Ultimate shear force V is equal to how much it is? 60 kilonewton. 60 kilonewton, which is equal to 60 into 10 power 3 Newton. The compressive pressure at the central axis FCP is given, correct? FCP is given as how much it is? 5 Newton per mm square. The characteristic cube strength of concrete FCK is equal to 40 Newton per mm square. Then the cover to be cover to the tension reinforcement is 50 mm. The cover is given. Cover is given as 50 mm. Okay. The overall depth is given as 250 mm. In that cover is 50 mm. Therefore, the effective depth will be how much? Therefore, the effective depth is equal to dt is equal to overall depth 250 minus cover 50, which is equal to 200 mm. 200 mm. Okay. Then what else is given? The characteristics tensile strength of steel syrups is 250 Newton per mm square. Fy is given. Fy is equal to 250 Newton per mm square. Okay. Design the suitable reinforcement at the section using Indian standard recommendations. Okay. Now we will follow the same steps. What is the first step? Calculation of ultimate shear force. That is directly given. Correct. Ultimate shear force. Step 1. Ultimate shear force. It is given on the problem only directly. That is Vu is equal to 60 kilonewton. 60 into 10 power 3 Newton. Okay. Then second step, calculation of internal shear resistance. Step 2. Step 2. Internal shear resistance. Shear resistance. Internal shear resistance. So we have the formula for that. That is VC naught is equal to 0.67 B into D into root of FT square plus 0.87 FCP into FT. Okay. So it is there in page number 46 of IS 1343 code book. The same formula I'm copying. Okay. In IS 13834 book, the formula is there. Okay. VC naught is equal to 0.67 B into D root of FT square plus 0.88 FCP into FP. IS 1343 1980 code book. Okay. Where FT is tensile stress. FT is equal to, we have the formula for that also, 0.24 root of FCK. So this formula is there in page number 46 only, or 48 also, in page number 40 also, 48 also it is there. 0.24 root of FCK, FT. Okay. Okay. 0.24 root of FCK, FT is equal to, here it is there. Substitute the value of FCK, that is characteristic strength of concrete, 0.24 into root of, what is the FCK value given? 40 Newton per mm square. 40 Newton per mm square. So FT is equal to, so the answer that you get is 1.52 Newton per mm square. 1.52 Newton per mm square. Okay. And FCP is given. FCP is required now in this formula. FCP is 5 Newton per mm square. FCP is equal to 5 Newton per mm square. See here, I have not added plus P sin theta because here the profile of the cable, okay, profile of the cable is not mentioned. If it is not mentioned means we have to assume it is a straight profile cable only. Okay. In the previous problem, he has given the inclination theta. Okay. Arc, the angle of the inclined at an angle of the arc of sine inverse of 1/6. That is why it was parabolic. It was understood that it is a parabolic cable, and theta was there. Okay, but in this problem, in this design problem, he has not given any angle. Okay, he has not given any angle. Therefore, the profile of the cable is assumed to be straight only. When the profile of the cable is straight, if you take the tangent, you will get 0 degree. There is no theta only. Therefore, I have not added P sin theta here. In the previous design problem, I have added P sin theta, correct? Plus P sin theta I have added. Here you can see why I have added means there is angle because it is a parabolic cable. But in this problem, theta is 0. So P sin theta will not come into picture here. If you want, you can write P sin theta and you can take that, you can assume that value as 0, no problem. Okay, better you do that. Plus P sin theta. Okay. Then FCP is equal to 5 Newton per mm square. Sin theta value is 0. Okay. The profile of the cable is not mentioned here. Okay. Assuming straight cable profile. Assuming the profile of the cable as straight, right? Theta will be 0. Therefore, P sin theta is equal to 0. Okay. This value is 0. 0. Okay. This way also we can do. Now you can substitute everything. In equation 1, you can call this as equation 1. VC naught is equal to, therefore the equation 1 becomes VC naught is equal to, what is the formula? 0.67 B into D. 0.67 B is 100, D is 250 into root of 50 square into root of FT square, FT 1.52 square plus 0.87 FCP into FT. Therefore, here it is 1.52 square plus 0.87. FCP is 5, FT is 1.52. So the answer you get is 50 kilonewton. 50 kilonewton or 50 into 10 power 3 Newton. This is the shear resistance of the beam. Okay. The ultimate shear force that is acting on the beam is 60 kilonewton, but the shear resistance is 10 kilonewton, 50 kilonewton. So for the remaining 10 kilonewton, we have to design the shear reinforcement. Okay, below you can write VU ultimate shear force or the shear resistance of the beam is less than the shear force that is acting on the beam. Therefore, the shear reinforcement has to be designed. Therefore, provide shear reinforcement. provide shear reinforcement. Okay, so we'll go to the step 3 now. Design of shear reinforcement. Design of step 3. Design of shear reinforcement. Shear reinforcement. Design of shear reinforcement. So here the depth of the beam is less, correct? How much it is? Around 250 mm is there. 250 mm is there overall depth. So you can go for two-legged stirrups. Okay, using below, right? Using two-legged 8 mm dia vertical stirrups. Vertical stirrups. The area of vertical stirrups will be how much? Pi d square by 5, pi into 8 square by 4, and two-legged means multiply by 2. The answer is 100.53 mm square. 100.53 mm square. Now we can calculate the spacing now. Spacing. First one is using the formula which is there in the page number 48 code book. Okay. This formula. Okay, using this formula. We'll copy this formula here. ASV by ASV is equal to VU minus VC naught 4 divided by 0.87 Fy into dt, which is there in page number 48 IS 1343 1980 code book. Okay, the ASB it is 100.53 divided by spacing is needed, that only we are calculating. VU minus VC naught. VU shear force acting on the ultimate shear force acting on the beam is 60 kilonewton, that is 60 into 10 power 3 Newton minus VC naught, shear resistance of the beam. We got it as 50 kilonewton. So 50 into 10 power 3 Newton. Okay, whole divided by 0.87 Fy 250 into effective depth is 200. Effective depth 200. Okay. So if you calculate for SV, you'll get the answer as 437.3 mm. 437.3 mm. Okay, this is the first calculation for the spacing. Second calculation is what it is. It is a 0.75 into dt. 0.75 into effective depth. 0.75 into dt is 200 we got. That is 175. Third calculation is 4 times BW. Here we have the rectangle section. There is no web here. So we will take it as 4B, width of rectangular beam. 4 into 100. That is equal to 400 mm. 400 mm. In the fourth calculation, see this 0.75 dt and 4 into BW dt, they are also there in page number 48 of the code book. You can just check it out in the code book. And last calculation is by using the one more formula, that is minimum shear reinforcement formula, which is provided in the same code book. Using this formula, we will calculate the spacing, that is ASV. I'll copy the same formula here. ASV whole divided by V into SV is equal to 0.4 whole divided by 0.87 Fy. Same page number 48 of the same code book, AS 1343 1980. Okay. Now substitute. ESP is how much it is? 100.53. 100.53. B is 250. into spacing is SV 0.4 divided by 0.87 into Fy is given as 250. Okay, therefore by this the spacing that you get is 218.65 mm, 218.65 millimeter. Now you got 4 different spacings. Out of all these spacing values, now you have to provide you have to take into consideration of minimum value out of all these 4 calculations. Which is the minimum value? 175 mm is the minimum value. So we have to go for providing the spacing of 175. Okay. So you can round it up to 170 mm. Okay. By considering the practical implementation of the reinforcement at the site, we can take it as 170 mm. Okay. Therefore, taking least value of above calculations, which is the least value we observed is 175. 175 mm, where you can write a final word that is provide, therefore provide two-legged 8 mm vertical stirrups at 170 mm center to center at the supports, and you can increase the spacing at the midspan and provide the same reinforcement two-legged 8 mm vertical stirrups at. So by considering the minimum shear reinforcement, we got it as 218 mm. So we can go for 210 mm at 210 mm center to center at midspan. Okay, as I said before, uh, the shear force will be maximum at the supports and it will be less at the midspan. That is why we are increasing the spacing of the shearers at the midspan, and we are providing uh, the required spacing at the supports by the calculation. Okay. Finally, you need to draw the reinforcement details. Just you draw it at the longitudinal section as well as cross section. Now write the reinforcement inside of the B shear reinforcement. At the support section, the spacing will be less, and at midspan, the spacing is high. Now I'm getting the shear reinforcement at the support. Now at the midspan, you need to increase the spacing like this. Okay. So here at the support, we have given two-legged vertical stirrups, 8 mm. Just a minute, I'll change it. Two-legged vertical stirrups, 8 mm dia at spacing of how much? 170 mm at 170 center to center. Here also same thing. Two-legged 8 mm vertical stirrups at 170 mm center to center. So at the midspan, two-legged 8 mm vertical stirrups at 210 mm center to center. Okay. In the cross section, how it will look? So these are the main reinforcement. Okay. Shear reinforcement will be okay. You write the cross sections of the beam. It is 200 by how much? What is the cross section given? 100 by 250. 100 by 250 mm. Okay. This is the cross section of the beam. This is ELS. Okay. Reinforcement details. So here you can see two-legged and right. Two-legged 8 mm dia stirrups. So reinforcement details. Okay. So to this problem is over. Okay, the design of beam for the shear is over, and model 4 is also over, students. In the next class, I'll be starting the model 5. Okay. To this, I'll end the class. Thank you, and we'll meet in the next class.